Hello, today we're going to study equating chemical reactions using the electron-ion balance method. Complex redox reactions can be equalized using this method. We will now look at the interaction between potassium permanganate and oxalic acid in the presence of sulfuric acid, and the reaction produces potassium sulfate, manganese CO4, CO2, and H2. So how does this method work? Step 1. To begin, it is necessary to isolate the electrolyte substance in this chemical reaction. If the substance is classified as an electrolyte, it will undergo dissociation. An example of this is seen with potassium and manganese CO4, where they will dissociate into potassium and manganese CO4 due to the solubility of all potassium salts. Additionally, oxalic acid will decompose into hydrogen ions and the resulting residue. Similarly, sulfuric acid, a strong electrolyte, will dissociate, leading to the dissociation of potassium and manganese CO4, while the decomposition of CO2 and manganese CO4 will result in potassium and manganese CO4. Hence, it becomes evident that this molecular equation should be converted into an ionic equation. The final representation appears as follows: that manganese CO4 with a minus charge plus CO4, charge minus and plus CO2, and plus CO2. The resulting equation is in ionic form. The potassium and CO4 ions are contracting because they are strong electrolyte residues. Now we need to see what happens in this case to our ions. The manganese CO4 turns into manganese ions, and the oxalic acid residue turns into CO2. Thus, we have two ions in changing oxidation degrees and charges. This stage is called stage 2, when we've identified which particles have changed charges and shapes. Then step 3. We have to write down two equations for the half reaction. Let's write down the first equation for manganese CO4. Manganese CO4 is converted to manganese ion CO2+. This is the first equation of the half reaction. And the second equation is CO4 turns into CO2. This then turns out to be step number 3. The next one step that needs to be done. We need to determine what is going to happen inside these half reactions. As we can see, in the first reaction equation, we have oxygen on the left side, but we don't have that element on the right side. How do we remove the oxygen from this reaction? Let's see. We have a medium, which is sulfuric acid. Then the rule of thumb applies. To remove the oxygen, we add hydrogen ions. The ones that come out in this case will be water molecules. Then inside the half reaction should be equated. Oxygen is 4, here it's 1. We put 4 in front of the water formula. And in front of the hydrogen formula, we put a factor of 8. What happened in the second reaction? Here we have 2 carbons, here we have 1. Let's equalize. Oxygen 4, and here we have 4. That's step 4. Next step. We need to determine how the balance of the particles has changed, what the charges were before and after these half reactions. Let's do the math. On the left side, we have a charge of +7, -1, +8, and on the right side, we have +2. To go from +7 to +5, we have to accept 5 electrons. in this half reaction, you get the acceptance of electrons. What's in the second half reaction? Here the charge is 2- and the CO2 molecule is neutral. Thus, the particle will give up 2 electrons. But as we remember, this notation needs to be done in this way. So, the first reaction is accepting electrons. The second reaction is giving up electrons. Then we bring the electron-ion balance scheme to a close. We write out the number of electrons given up and electrons accepted over the line. We'll write down 5 here and 2 here. Then, to balance this number of particles, we swap them around. We call the process that goes first reduction. And that's the process that happens for the oxidizer. The second process is called oxidation. And the element itself is called the reducing agent. Then the next step is to write down the equation after we've added our multipliers. We multiply the left side of the first equation by a multiplier of 2. We get 2 manganese, O44-, plus 8 times 216H plus. The second half reaction we have is multiplied by 5, so we get 5 C2O444-. In the total number of electrons we have on the left side, we have the acceptance of 10 electrons. And on the right-hand side, with the multipliers, we have 2O444 manganese plus 8 H2O plus 10 C2O44. And the total number of electrons that are given up will also be 10. Then we need to give, if there are any like ones in these equations. Like ones are particles that are the same. In this case, it could be hydrogen, for example, if it were left and right, or water if it were left and right. But as we can see, there are no similar particle equations here. So this step is missing. And then there's one last thing to do. To transfer our coefficients into the original equation that's been set up. 2 in front of potassium manganese O44, we have 16 total hydrogen ions in time. Now in front of the oxalic acid formula, we will put the coefficient 5. Then manganese, we have in this case 2 on the right side, manganese CO444. 8 will be to water. 10 in front of CO44. Now let's do an internal equation. Potassium on the left side is 2, and on the right side is also 2. Now CO44 on the left side, the acid residue is 1, and on the right side it comes to a total of 3. In front of the sulfuric acid formula, we put the quotient 3. In this way, we check how many hydrogen ions we have. It turns out in oxalic acid they will be 5 times 210 and more hydrogen, which is in the acid 16. That's what the 16H plus particle is made up of. Now on the right hand side we have no more particles that need to be checked. It remains to check by oxygen. It is necessary to do it in order to check whether all the coefficients are correctly arranged. Let's check on oxygen. On the left side, 8 plus 20 and another plus 12. That makes 40. Check the right side, 4 plus 8 plus 20 plus 8. We also get 40. Our equation is equated. I would like to say that this method of equating seems very difficult at first, and there are quite a lot of entries. But this method works very well in complex redox reactions. In the next lessons, we will practice equating such interactions. Goodbye.